Welcome to the course on RF transceivers, Unit 1, CMOS Physics, Transceiver Specifications and Architecture. Topic is Transceiver Specification, Two-Port Noise Theory and Noise Figure. The objective of this presentation is to investigate the principle of two-port noise theory and its practical application to optimize the noise performance in the electronics systems, and then to investigate the noise figure and its significance in optimizing electronics and communication system performance. This is the example for two-port network. I1 is the input current to the input port, and then I1 current is also leaving in the bottom terminal. Similarly, at the output port, I2 is the current entering, I2 is the current entering, and the same current is leaving the I2 output port as I2. Then V1 is the voltage at the input terminal, V2 is the voltage at the output terminal. So this is the example for two-port network. So any circuit or any device can be characterized in terms of two-port network. So it consists of several parameters. Some circuit may be represented by a specific parameter, and some other circuit may be represented by more than one parameters. So now a particular device generating the noise is represented in terms of two-port circuit. So that is noisy two-port circuit. That means particular circuit itself, device itself is generating noise. So we'll represent that characteristics in terms of noisy two-port circuit. And then the same two-port network can be modified like this, like introducing the parameter without noise and bringing the noise outside the two-port network as a noise voltage and then noise current. Introduction to two-port noise theory. Definition of two-port noise theory. So two-port noise theory is the fundamental concept in electronics engineering that deals with analysis and characterization of noise in two-port networks such as amplifier, filter, and communication systems. Importance of noise analysis in electronic system. So we know that in communication, noise can significantly impact the performance of electronic devices and communication systems, affecting our signal quality, so that the data transmission rate and then overall system efficiency. So ultimately, the rate at which we are transmitting depends on the effect of noise, because we'll always consider signal to noise ratio. If the signal to noise ratio is better, we can transmit data at larger rate so that we can increase the overall efficiency of the system. Then overview of noise sources in two-port network. We know that there are various noise sources. They are thermal noise, short noise, and then flicker noise. Already we have seen the introduction about these noises. Whenever the thermal noise is directly proportional to the temperature, and then the device such as transistors will generate short noise. And then when we operate the devices at very low frequency, there may be the effect of flicker noise. So these are all the noise sources in two-port network. So these noises contribute to the overall noise in two-port system, and then understanding their characteristics is important for noise analysis. Noise parameters and models. Introduction to noise parameter. So to define a noise, we will use noise figure and the noise figure density. These are all the important parameters used to quantify the amount of noise introduced by the device. The problem is already the signal is coming with some noise or interference. When we are processing that signal, our processing system itself will generate some noise. So that has to be analyzed. So To define how much noise is generated by the device, we use the parameter called noise figure or noise factor. So in the upcoming slide, we will see very deeply about what is noise figure. So this noise figure provide crucial information about noise performance of two-port network. Then mathematical representation of noise in two-port devices. Noise in electronic system can be modeled using noise current, and noise voltage sources, leading to the calculation of noise parameters and the overall noise figure of the system. Interpretation of noise parameters in amplifiers and networks. Understanding the noise parameters helps in assessing the noise performance of amplifiers, filters, and other two-port devices, enabling the engineers to optimize the system design. Noise matching technique. Significance of noise matching in reducing the noise figure. Proper noise matching is essential to minimize reflections. We know that whenever we operate at high frequency, we have to consider not only the forward waves, we also will consider the reflection waves also. So that time we have to reduce the reflection waves in order to minimize the effect of noise. So and enhance the signal to noise performance, particularly in high frequency applications. Then impedance matching for optimal noise performance. Impedance matching technique can be employed to achieve the maximum power transfer. We know that matching is generally used to achieve the maximum power transfer along the line. And then we also try to reduce the noise so that the noise figure will be very minimum. That means lowest noise figure, so that the overall performance of the system will be improved. So for a better system, the noise figure should be very low. That means if the system adds less noise, very less noise, it will produce a very less noise figure. If the system adds more noise, the noise figure will be more. Next, matching networks and design consideration. Various matching network topologies and design considerations are explored to effectively minimize the noise and finally to enhance the signal to noise ratio in the two-port network. Noise characterization and measurements. Noise measurement technique. Noise figure measurements are commonly performed using Y factor method or using noise figure analyzers to determine the noise contribution of the device or a circuit. The noise figure analyzer and its application. Noise figure analyzers are specialized instrument used to characterize the noise performance, providing variable insights into the system behavior and helping engineers to make informed decision about the effect of noise. Then practical noise measurements, challenges and solutions. Real world noise measurements can be affected by various factors such as the environmental condition and then system complexity. Application of two-port noise theory. Noise analysis in communication system. This two-port noise theory finds various application communication system where I will try to where minimizing the noise figure is the crucial factor for maintaining the signal integrity and then maximizing data throughput. And the noise consideration in low noise amplifier and mixers. The, the term noise figure is very important in case of low noise amplifiers. Low noise amplifier is an amplifier which adds less noise in the process of amplifying the incoming signal, because whenever we operate with a very low level signal, if our system itself, say I'm operating with some signal power and then I create some noise, my system creates some noise. If this noise is higher, say for example, I'm operating with less signal power, but in the process of amplifying the signal, if I'm introducing more noise, what will happen? The signal to noise ratio will become very poor, so that we cannot get any significant information from that signal. So the term signal to noise ratio is very important when we deal with the low noise amplifiers and mixers. So Low noise amplifiers and mixers are crucial components in communication system, and then their noise performance directly impact the overall system sensitivity and noise figure. So we will use LNA where our signal level is very, very low. Say, for example, we try to receive a signal from the dish antenna. Then we will use LNA, low noise amplifier, because the signal coming from the satellite will be of very, very, very weak power. So in terms of picowatt, so from that signal we have to get some significant information. So when we are trying to deal with those information, when we are doing the processing demodulation procedures, we should not add extra noise in that. So low noise amplifier finds application where we need to operate with the low level signals, low level power signals. Introduction to noise figure. So noise figure is the important parameter in electronic system to measure the impact of noise on signal quality. Measure the impact of noise signal quality, and it also gives how much noise is added by the device. Noise figure is the measure of how much noise is added by the device. If the system adds less noise, then noise figure will be low. If the noise figure value is low, that what is the meaning? The system adds less noise. If the noise figure value is more means if the system is adding more noise, then noise figure value will be very high. Noise figure value will be, so it is a direct measure of how much noise is added by the system. So the lower noise figure indicates the better performance. Why? Because the noise figure is low means that particular system is adding less noise. So we always aim for low noise figure. So and that too in case of sensitive applications, like whenever we try to deal with very low power signals, definitely we need to have low noise figure. So this is the formula for noise factor. Noise factor means what is the signal to noise ratio at the input, then what is the signal to noise ratio at the output. We take a system, say we take some system at the receiver side, we receive some signal, then the input to the system, receiver system, we will call it as SI by NI. Output of the system, we will call it as SO by NO, where SI is signal level at the input, NI is noise level at the input, SO is signal level at output, NO is noise level at the output. So this system may provide some gain or attenuation. Say for example, if the system is providing some gain or attenuation, what will happen? SO by NO, say our SI also will be multiplied by gain, NO also will be multiplied gain. But in this process, what will happen? In the process of demodulating the signal or doing the process of doing signal processing at the receiver side, the system itself, the system consists of like mixer, amplifier and other things. The system itself will add some noise that we will denote like N system. So what happens? This N system is added with this N system. Now what happens? If that N system is 0, that means if the system is not adding any noise, if N system is 0, what happens? SI by NO is same as SI by NO is same as SI by NO is same as SO by NO, so that our noise figure will be 1. Our noise figure will be 1. Okay, so our noise figure or noise factor, they will be used interchangeably when you take log base 10, and then multiply with 10, then we will represent in terms of decibel. So in terms of number, it is 1. So noise figure is 1. So noise figure or noise factor is 1. Then what happens if you increase N system? That means the noise added by the system increases. If the noise added by the system increases, what is the problem? So the denominator increases. So okay, so if you increase n system, so this increases. Okay, so when it increases, definitely what happens to SO by NO? SO by NO will decrease. SO by NO, SO by NO, when we increase the denominator here, definitely this term will decrease. So what happens when SO by NO decreases, then noise factor will increase. So that means when n system increases, definitely the noise factor will increase. Okay, so more the n system noise added by the system, more will be the noise factor. That's why we are telling, if the noise figure is very low, then the noise figure is very low, that means the system is adding very less noise. So that is a good system. That is a good system. So the low noise figure is the important in applications where we operate with the weak signals. If you want to detect weak signals and transmitted, then in those cases, definitely we need to have low noise figure. Then it ensures the desired signal is distinguishable from the background noise. Okay, because already signal will be coming along with the noise. If our system is not able to identify the signal, if our system is adding more noise, then we cannot distinguish the signal from the we cannot get any useful information from the signal that is already with some noise. So then it is used in industries like telecommunication, medical imaging, and then radar. These industries heavily rely on low noise figure for accurate data acquisition. Then if there are more than one system, say system 1 and then system 1, system 2, system 1 is having nice figure of n of 1, system 2 is having nice figure of nf2, then what is the overall noise figure? This n of 1 will provide how much noise is added by the stage 1. This nf2 is the indication of how much noise is added by stage 2. Then what is the overall noise? What is the overall noise? The formula here is the total noise figure is nf1 plus nf2 minus 1 divided by AP1. AP1 means gain of the stage 1. Gain of the stage 1. The same thing can be extended if there are three systems, that is NF3 minus 1 divided by AP1, then AP2. AP2, the power gain of two stages. So similarly, this formula can be extended. Then quickly, we'll see one concept here. Say, for example, I have two systems, one with noise figure of 10 and another with noise figure of 1, then what is the overall noise figure? Or otherwise, if I'm interchanging the system like this, then what is the overall noise figure in two different cases? Say this is case 1 and then case 2. Again, we cannot arbitrarily interchange the system. Whenever, even if you interchange, if there is no change in the overall operation, we can interchange the system. Then quickly we will see what is the overall noise figure, and also we will assume that both are having same gain. This is also having gain 10, gain 10. So both the systems are having gain 10. Okay, so now what is the formula? The overall noise figure formula is f1 plus f2 minus 1 divided by 10. So 10 plus 10 plus nf is 1. So this is simply 0, or for simplicity we will take 2. Okay, so if it is 2 minus 1, then it is 0.1, then it is 10.1. Now what happens here? Here the second case, so 2 plus 10 minus 1 divided by 10, 2 plus 0.9, 2.9. So now in the first case, the overall noise figure is 10.1. whereas in the second case, the overall noise figure is 2.9. So we know already that if the noise figure is very, very low, then that particular system is a good system. So this combination is good. As compared to the case 1, the second case is good because it is having overall noise figure of very less value, that is 2.9. But only one condition is if you are allowed to interchange the systems. That means even if you interchange the system, there is no change in the overall operation, we can do that. So whenever you have flexibility, always you should try to put the system with the low noise figure in the first stage and the system with the high noise figure at the second stage. That is the important understanding. Factors affecting the noise figure: semiconductor materials and fabrication process. Different materials and manufacturing techniques can introduce varying level of noise. Temperature of the device. Already we know that there is a concept of thermal noise that is directly proportional to the temperature. The thermal noise power is directly proportional to the temperature at which we are operating. So noise performance can change with the temperature. So we need to have proper thermal management in a place where we are operating with our devices. Then impedance matching at input and output. So poor impedance matching can lead to higher noise figure. So due to signal reflections, this mainly will occur at a microwave frequency. That is, whenever we are operating with a higher frequency, there comes the concept of reflections. Then it can lead to the higher noise figures. Then excessive noise generated by active components. We know that there are some noises that will be short noise and all will be generated by active devices like amplifiers, oscillators. That can also contribute to the additional noise in the system. Noise figure management and comparison. Measuring noise figure involves comparing output noise, signal to noise ratio, and then input signal to noise ratio. Mostly output signal noise ratio will be less than the input signal noise ratio because of the noise added by the system. We always try to reduce the noise added by the system. Then techniques like Y factor method or using the specialized noise figure meters are commonly employed. Noise figure values can be compared for different components, okay, to select the best suited devices for a specific application. Conclusion: noise figure is a critical metric for evaluating the noise performance of the electronic system. And then achieving low noise figure is always essential for sensitive applications with weak signal, Understanding the factors affecting the noise figure helps in optimizing system design and component selection. Then accurate measurement and comparison of noise figures help in achieving the desired performance for electronic devices and applications. Reference: R of Microelectronics by Razavi. Thank you.